Hi, today we're going to be talking about lesson 2.2, limits involving infinity. So we're going to look at limits as x approaches positive and negative infinity. We're going to look at the sandwich theorem again. We are going to look at some limits as x approaches some value that gives us a vertical asymptote. And we're going to refer to a lot of these limits as x goes to infinity as end behavior models to try to simplify the way that we think of limits as x goes to infinity. So let's take a look. Let's think about what we did last time with. Most of our limits went from x approaching some value c. So the difference between last lesson and this lesson is most of the time we're going to be talking about limits approaching infinity and negative infinity. So just try this really quick as you look at this graph, the graph of g of x. Go ahead and say, what is the limit of g of x as x goes to positive infinity? And then say, what is the limit as g of x, or of g of x as x goes to negative infinity? So hit pause, see if you get this right. Okay, hopefully you said that the limit of g of x as x approaches positive infinity is equal to 7, because as I'm coming over the graph up to positive infinity, I'm approaching that. They've even got the horizontal asymptote drawn there, right at that 7. Okay, labeled on the graph there. And hopefully you said for the other one that one, as we approach negative infinity, that one's going to that horizontal asymptote at 3. So here's your definition of a horizontal asymptote. If you want to write it down for your notes, please do. Just hit pause. Moving on to the sandwich theorem. The sandwich theorem we talked about last time. So whenever you're doing a sandwich theorem, you want to try to simplify it as much as possible. So I see cosine x here, so I'm going to go ahead and start writing this out as I know that the cosine stays between negative 1 and 1. Okay, well, I also know if I make it a negative cosine, it'll do the same thing, so that gets that negative in there. Then, to trying to get back to this original problem, if I go ahead and make or add 2 to both sides, 2 plus negative 1 is 1, less than or equal to 2 minus cosine of x, less than or equal to 1 plus 2 is 3. So that's adding 2 to both sides. So now I've got my numerator of the limit I'm trying to find. Okay, and now I need to just divide by something. Well, I didn't break any rules because I added 2 to everything. So if I divide all 3 of these, I haven't broken any algebraic rules. So I'm going to say that 1 over x plus 3 is less than or equal to 2 minus cosine of x over x plus 3, which is less than or equal to 3 over x plus 3. So if I look at the limit of 1 over x plus 3 as x goes to positive infinity, if I think about that, if I do 1 divided by a huge number plus 3, so really it's just 1 divided by a huge number, that is going to approach 0. So my limit is equal to 0 here. And I also look, if I do 3 divided by a huge number, infinity, I know that's also equal to 0. So I can just write 0 is equal to the limit as x approaches infinity of 3 divided by x plus 3. Okay, since both of those are equal to 0, then I've just sandwiched in, because I know this is between the two or equal to the two. It has to, sandwiching in between one value is just that value, so therefore the limit of 2 minus cosine of x over x plus 3 as x goes to infinity is equal to 0. So you go ahead and give this a shot. Hit pause. Okay, hopefully this is what you got. If you didn't hit pause, try to figure it out. But I'm assuming most of you got that. If you have any questions, bring them into me, please. Next. Okay, properties of limits as x goes to positive or negative infinity, same as the other properties. So we're not going to spend much time. Please hit pause and write them down if you'd like. But we're going to move on. Second example. Find the limit of y as x goes to infinity and the limit of y as x goes to negative infinity. So this is kind of using some of those properties, how we can simplify this. So I know that if I just split this up, I could make it y equals 2x over x plus sine of x over x. Okay, and I know here if I took the limit as x goes to infinity and I plugged it in, I would do the limit of 2x over x as x goes to infinity, which is equal to, if I think about this, the x over x, those x's will end up canceling. Okay, so it's really the limit as x goes to infinity of 2, a constant, which is just equal to whatever the constant is. And then if I do the limit as x goes to infinity of sine of x over x, well, if I look at this one and I do the sandwich theorem with sine of x over x, I'm going to see that that one is equal to 0. If you need to hit pause and check me on that, do. But then I can write, I know that if I have the sum of two things, of two limits, they're equal to the sum of their limits, so it's just going to be equal to 2 plus 0, which is equal to 2. Okay. As I go to negative infinity, if I just change this, the same thing is going to happen. Whether I'm going to positive or negative infinity, it doesn't matter. They're both going to give me a 2 and a 0. So in this case, that doesn't happen always, but for this function here, it's going to give me the same answer. Okay, you go ahead and give this a shot. Hit pause, please. Okay, so hopefully you found that the limit as x approaches infinity of y is equal to 5. Okay, if we look at this again, just go through 2 over negative infinity is still going to be 0. Negative infinity with of a constant 1 is still going to give you 1. The x's cancel there, so you have a constant. That's going to be 5 still. So negative infinity, negative 1 divided by negative infinity is still 0. So the negative infinity doesn't change from the positive infinity. So here, both positive and negative infinity both have the same limits for y. Okay, so we just have talked about last time. We saw this a couple times last time of a vertical asymptote, but a vertical asymptote is when you're approaching an actual value like a here. The limit of f of x as x approaches a from the right equals either positive or negative infinity. That is a vertical asymptote. Or if you're coming from the left and the limit approaches positive or negative infinity, that's a vertical asymptote. So there's a definite. Find the vertical asymptote of the graph of f of x here. So here we want to see, is there some value that a limit will go to infinity? Usually something like this is where you have a number divided by infinity. So if we look at this, we do have the higher power in the denominator, we do have an x in the numerator, but an infinity squared is way bigger than a just plain infinity, so it will end up dominating this function. So when we're talking about end behavior models, which is a good way to think about limits, really this model can be looked at, and we'll talk about this towards the end, some of our last examples, but this can really be looked at as negative x over 2x squared, where that x will cancel with one of the x's down below and just leave us a negative 1 over 2x. So thinking about it this way, it's easier to look at this example and go, okay, I know that 1 over 2 times 0, 1 over, that's going to give me a negative infinity. So I know here that the limit as x approaches 0 from the left or the right, it doesn't matter which side you're, well, that's not true. We do need to talk about this. So we'll say the limit as x goes to 0 from the left. Okay, so we'll do the left first, which is negative 1 over 2 times a negative 0. Well, that shouldn't make a difference. Positive or negative, it's 0, so never mind. So 2 times 0. Okay, that gives me negative 1 over 0, which is equal to negative infinity. Okay, or if you're approaching it from the right, it'll still give you a 0, and it'll still be negative infinity there. So we know that means that there is a vertical asymptote for this graph at 0. Okay, you try this. Find the vertical asymptote of the graph of f of x. So on this one, we still want to find what gives us a denominator of 0. So we want to find 2x plus 4 equals 0. And solve this, you should get negative 4. You should get x equals negative 2. So x equals negative 2 is going to give me that value of 0 in the denominator that makes this go to infinity, basically. We do want to look at the limit from the left and the right, though, so let's take a look at that and say, okay, the limit as x goes to negative 2 from the left of x squared minus 1 over 2x plus 4. So if we think about that, the limit from the left, let's just try a number like 3. If we used a 3 over here, it would give me 3 squared minus 1 is an 8, and then 2 times negative 3 is negative 6, plus 4 is negative 2. So we've got 8 divided by negative 2. That's going to give me a negative value. So this one should approach negative infinity. And then as I look to the limit as x goes to negative 2 from the right of x squared minus 1 over 2x plus 4. So let's just try negative 1. If I did negative 1 squared, I'm at 1 minus 1 is, 1's not a good number. Maybe we'll try 0. No, 0 is not a good number either. Well, let's just do negative 1.2. If I pop that into my calculator, okay, let's just use negative 2.1 because we want to see it's got to be close to the asymptote. Probably before I should have chosen something like negative 2.1, or I guess I should do negative 1.9. Sorry about all those mistakes. I just realized what I was typing into the calculator. I forgot to square that x squared in the numerator. Okay, so looking at x, the limit as x goes to negative 2 from the left, I typed in negative 2.1 and I got a negative 17.05. So, as we get closer to to 2, it'll keep getting a bigger negative number, so that gives me negative infinity. As I put in a negative 1.9, so from the right side, that gives me 13.05. If I got closer and closer to negative 2, it would be getting bigger and bigger, so this one's equal to positive infinity. So this is just a situation that gives you one side is negative infinity, the other side is to positive infinity. So a good one for you to see. You can graph it to take a look at the asymptote there, see what it really looks like. All right. Find the vertical asymptote of the graph of the secant. So secant is 1 over cosine, so we can just look at this graph, and it's not labeled very well with trig stuff, but we can kind of see the asymptotes are going to be here, 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 and so on. So it's somewhere between 1 and 2. Well, if I think about trig, think about cosine and what the secant really is, 1 over, I'm trying to get a value of 1 over 0 to give me that positive or negative infinity. So when is cosine equal to 0? Cosine is equal to 0 at pi over 2. Cosine is equal to 0 at negative pi over 2. It's equal to 0 at 3 pi over 2, and so on. One way that you could write that would be to say that the limit of f of x, which is the secant of x, but I'll just do the limit of f of x as x approaches a is equal to plus or minus infinity, depending on if you're from the right or the left of a. And then you just still have to define a. So a is equal to pi over 2. We said pi over 2, 3 pi over 2, 5 pi over 2, and so on. Or you can go to the negative side, negative pi over 2. So if we just add k times pi, where k is any integer, that should work just fine. Okay, we've talked about end behavior models. I wanted to show you why we talk about end behavior models. As you're approaching infinity, you can see the difference between these two graphs. The first graph goes up to 1, 2, 3, 4, 5, 6, 7 as far as your x-axis, and about 7 is your y-axis. The second graph graphs the y-axis up to positive and down, or up to infinity and down to, or not infinity, 1 million and down to negative 1 million. So you can see we're getting really huge. These are the same exact two graphs. You can see though that once you're talking about huge numbers, we're getting to the same model. So the end behavior model is always going to be with polynomials. Whatever the highest exponent is, that's what it'll look like. If it's a power function polynomial looking one where you've got a numerator and denominator, you're going to have to actually do a little bit of division with the highest exponent piece from the top divided by the highest exponent from the bottom to be able to find out what your end behavior model is. There's a definition of the end behavior model. It makes sense if you were to divide these two, like I just said, the limit as x goes to infinity of 5x cubed minus 4x squared, and so on, divided by 5x cubed. Because we're approaching infinity, the x cubes dominate all the others. So I didn't even have to write the others because I know that even that negative 4x squared is going to go away. It's going to be dominated. If I look at these, then all that I'm left with is 5x cubed over 5x cubed. Okay, that's the same thing, so that does equal 1. So this limit is equal to 1. Okay? here's an example. So like I said before, we take the top exponent of the numerator and the top exponent of the denominator and we look at those. So this goes to, I'm looking for negative x to the fourth over x squared, which simplifies to negative x squared. So I would say that y, or that g of x equals negative x squared is the same end behavior model. It looks the exact same as you're going to positive or negative infinity as f of x there. Part B looks a little bit different because we have not just a polynomial, we have an exponential here with it too. So we've got x squared plus e to the negative x. Well, if you think about that, as we approach, so if we take the limit as x goes to, we'll start with negative infinity, okay, of x squared plus e to the negative x. So if we look at this, this is going to give us, if I go to x squared, it's going to give me a big number if I put infinity in there, but it's going to be dominated. Infinity is going to be so much bigger. Like, let's just put negative 1 million in there for x squared. That's going to give me a big number, like 1 times 10 to the 12th power. If we do e to the negative infinity, which is positive infinity, or think about it just a big number, if we did negative 1 million, e to the negative 1 million is, e to the 1 million is too big even for your calculator to handle. I just did e to the 100. E to the 100 is 2.68 times 10 to the 43rd power. So it's so much bigger. We're talking a huge number. I don't even know what it is, but we're talking to the millionth. It's so much bigger than 1 million squared that it just completely dominates that and basically makes it go away. So if we're looking at this, it's the same thing as if we just looked at the limit of x going to negative infinity of e to the negative x. So you can see exponentials dominate any type of polynomial that we have. So there you can see that. And this was equal to the limit here, not that we need to. The answer here is e to the negative x is our end behavior model. But if we looked at negative infinity, that would take us up to a positive infinity. Okay, but if we looked at it from going to the right, so now if we look at going to the right, the limit of x squared plus e to the negative x as we go, as x approaches positive infinity, well, now it's going to be a different story. We've got a huge number squared plus e to the negative huge number. Well, a negative exponent really means 1 over that, so that's really going to go away to 0. 1 over a huge number is 0, so this one, if we're going to positive infinity, is actually better modeled with x squared. So this one's interesting. You have two situations. One to negative infinity is modeled better with e to the negative x, but if you go to positive infinity, x squared models this better. Okay. You give this a shot. Hopefully this is what you got. For the top one, again, highest exponent dominates the rest, so it's negative 4x cubed is the end behavior model. And the bottom one, sine, even if as you're going to infinity, it's going to bounce between negative 1 and 1, so that's a small number compared to x squared. X squared just dominates this function. Last example, use the graph of f of 1 over x to find the limit as x goes to infinity of f of x. So here's an example of the cosine of 1 over x. That's a weird function to look at, so it's kind of odd. You can see though that it does approach, well, the axis isn't labeled very well, it's kind of hidden. It says 0.2 as those dashes for the vertical axis, so it's going up to, it looks like 1, so it's bouncing, which makes sense. Cosine bounces between 1 and negative 1. So as we go to infinity, you can see that looks like it's probably going to approach that 1. Well, you can take any of these functions. What this is saying is you can take any of these functions, and if you want to see what they're going to as x approaches infinity, if you do f of 1 over x, so cosine of 1 over x changes to cosine, and instead of going to infinity, if you look at as you approach 0, so we're going to say here that the limit as x goes to positive or negative infinity of cosine of 1 over x is equal to the limit as x approaches 0 of the cosine of x. So if you look at that, you can see as we go to 0 on the cosine function, that approaches 1. That works for all the functions. You need to be more specific usually and say from the left side compares to negative infinity, from the right side of 0 compares to positive infinity. That takes care of this video. I hope this was shorter than the first one. And I know I messed up a couple times in there, but I'm not going to fix this one because I'm still getting used to this program. I'll try to edit them as we go from here on. Go Eagles!